Amedeo Avogadro, the Italian physicist that gave us Avogadro's number, which defines the mole, that number has its basis in what's known as Avogadro's principle. And this principle states that when you have two different gases that are at equal temperatures and pressures, equal volumes of those gases will have the same number of molecules. And so the question is, why is this true? And to answer this, we need to consider and go back and remember the factors that influence the pressure, or the magnitude of the pressure that's exerted by a given gas. Those two factors were the force of each collision of the particles that make up that gas, and the number of collisions that are occurring within the particles of that gas. Well, the force of each collision is related to the kinetic energy of the particles. And if the two gases are at equal temperatures, that means that their kinetic energies are equal. So the force of each collision, that's taken out of the equation. And so the only other factor that's going to impact the pressure is the number of collisions. And so if we're assuming that the pressures of these two gases are equal, and they're in equal volume containers, the only way that you're going to be able to have those two gases have the same number of collisions of particles and therefore the same pressure is if there are literally the same number of molecules present in each sample. If we have two different gases and they're both at standard temperature and pressure, then 1 mole of each of those gases will have the same volume. And so to calculate what that volume is going to be, we need to know two things: the molar mass of the substance, and we also need to know its density. And the reason we choose those two quantities is because not only do they contain the units that we're ultimately going to want, a measurement of moles and a measurement of volume, liters, but also they have in common units of grams. And so that's the common factor, that's the bridge between the two. So we'll set these two values up in a factor label problem such that we can cancel the grams out. So if we take oxygen, oxygen has a molar mass of 32.00 grams. How do we get that? Well, to find the molar mass of a substance, you take the elements that are present in the formula, find their atomic masses on the periodic table, and then multiply that mass by whatever subscript there may be. So in this case, if we look for oxygen, to 4 sig figs, we get 16.00 times the 2 in the formula gives us 32.00 grams of oxygen per 1 mole of oxygen. Oxygen's density is 1.43 grams of oxygen per liter of oxygen. And so if we cancel the grams out and do the division, the units that we're left with are liters of O2 per mole of O2. And solving the problem, we have 3 sig figs based on the mass. Therefore, our answer comes out to 22.4 liters of oxygen per 1 mole of oxygen. If we do the same operation for a different gas, say hydrogen this time, hydrogen's molar mass, taking the mass of hydrogen off the periodic table, 1.008 to 4 sig figs, times the 2 for the 2 subscript in hydrogen's formula, we get 2.016 grams per mole of hydrogen. Hydrogen's density is 0.0899 grams of hydrogen, and so setting that density up as 1 liter over 0.0899 grams of hydrogen, grams will cancel, and once again, when we do the math, we're left with 3 sig figs, and we find that hydrogen also has a volume of 22.4 liters per 1 mole. And so the thing to note here is that even though we're talking about two different gases, one which is about 16 times heavier than the other one, regardless of that difference in mass, 1 mole, 6.02 times 10 to the 23rd molecules of each of these gases will occupy the same exact volume as long as we're at STP. That 22.4 liters per mole is only a valid value when our volume is measured at standard temperature and pressure. If it's not measured at standard temperature and pressure, then we need to use our other gas laws, Boyle's law, Charles' law, to correct the volume to standard pressure, standard temperature, in order for us to be able to legitimately use 22.4 liters per mole. So what volume at STP would 4.10 moles of carbon dioxide occupy? Well, we start with our original value, 4.10 moles of CO2, and because we're at STP, we need a conversion factor that's going to include both moles and volume. And we have molar volume, which we can use so long as we're at standard conditions, and in this case we are. So we're clear to use the 22.4 liters per mole, and we want to set that up so that the liters are on top and the moles are on the bottom. Why? So that the moles of CO2 will be able to cancel out, leaving us with liters. And now that we're in the units that we want, we need to carry out the operation, which here is multiplication. 3 sig figs based on our original amount of carbon dioxide. The 22.4 liters per mole is a defined value, so we ignore it for sig fig purposes. And our answer should come out to 91.8 liters of carbon dioxide. If we're asked to find the number of moles of a gas, helium in this case, that are present in 45 liters of helium at STP, once again we start with what we're given, and so long as we're at STP we can go ahead and go straight to our molar volume conversion. In this case, the 22.4 liters would need to be on the bottom so that the liters of helium can cancel out. The 1 mole of helium would go on top, liters cancel, and when we solve 45.0 divided by 22.4, we come up with an answer of 2.01 moles of helium.